Okay, so in this example, we come back to our bottle, but this time we don't want to create drops on the outside, but bubbles on the inside that move up. So we have our very simple bottle here because this is pretty easy to work with. This is why I use it. Of course, if you have a more complex geometry, you might run into some problems though, because this is just, a single wall, which makes it easier to work with, as we will see in a second. Now, before we move on, as usual, let's actually check with a Tommy the size. And in the last example, I didn't care about the scale, but this time I will, so that we get used to this. So let's transform this down so that it roughly makes sense. And thanks, Tommy. And then what we want to do is we want to kind of fill this thing with some liquid. So this is really just the glass outside, but we want to have an inner geometry that represents the liquid. Now, you could use a clip for this by just cutting off a part of our bottle, so something like this, and then we just turn this around. There you go. And then we have, unfortunately though, a hole at the top, so maybe we can fill this with a polyfill, and maybe triangles or whatever works for you. Maybe create literal fan, and then we have to turn off the deform patch, and then you have something like this. That's one option. Another option could be that we use a Boolean for this, with a single box, where we just want to find the intersection area of this box with my bottle here. And let's actually set this to intersect so that we get the inside area. And as you can see, this would have worked as well. Now, sometimes you might run into a problem because the bottle is actually not closed. To be honest, I'm kind of surprised that this worked. So keep in mind, sometimes you might have to use a polyfill before you put it into the Boolean to make sure that this is actually a closed geometry, and then it will work for sure. And here you can see the idea. We have now an area that defines some liquid. I'm not sure which way I go. I probably take the clip version, but as you can see, there are multiple solutions to this. So what we want to do now is we want to emit bubbles in there, and they will be emitted everywhere inside. So how do we do this? If we just take a pop network directly, what we will end up with is points on the outside. That's not what we want. We want the points to be scattered inside, and we already know how to do this. With a normal scatter, you would use an ISO offset. So that means you can use the same for a pop source. So let's just turn this thing into a volume. Let's make sure we have a proper resolution for it to represent the shape correctly. And then what you will see is that we will scatter in that volume, and we have a lot of points. Maybe a bit too many, so let's lower the number. Maybe to 50. Yeah, maybe a bit more, maybe 100. Yeah, that doesn't look too bad. Now, of course, what's a bit boring is that they stay where they are. So let's make sure that they actually move. Now, in this case, we can actually use a gravity that we just turn around. And once again, what you see here, it's not always about recreating the reality one-to-one. Keep in mind, we're not physics. We are entertainer. We create media. So we use the tools the way we see fit. So what I can do, instead of making the points fall down, we just move them upwards. So let's try 1. Yeah, it doesn't seem too bad, right? It feels already like bubbles moving up. Now, you could have set this by setting the velocity directly, but the advantage of using a force here is that the points will start with no speed at all and then will slowly accelerate, which will feel much more natural. And this is why gravity, or you could have used a pop force as well, is a pretty good choice here. So let's keep that. The speed is pretty good, actually. And now let's have a look at a couple of problems, of course, because the first thing is, as we can see when we show the bottle, our points here will fly out of our bottle into infinity. Now, the first thing you might think you could try, and you're right, of course, we can change our life expectancy, maybe something to 1 and 0.5 with a life variance. And that's still way too high, so maybe 0.3 and 0.1. Yeah, that's better. But even if you're really careful, of course, you can imagine it's very tricky to kind of nail the exact moment they should die based on your geometry. So this will, not end well if you do it this way. It will be very tricky. So what you can also do is you can just, brute force the whole thing in. So for example, we could check at which height we want to delete it. Of course, you could do this procedurally as well. But in this case, I do it a bit simpler by just putting here maybe a grid or something and move it where I want it to be, maybe somewhere here. And let's just check the position in space. It's 0.2. So yeah, maybe 0.1 or something. So I just take this number and I could steal it from here, but I will not do this. I will just type it in directly. I could just use a pop wrangle, for example, and just hard code this edge in and say, okay, listen, if your position of your current point in Y is higher than 0.19, which you can of course also put onto a parameter. So maybe let's call this channel height. And then we put the number down here into our own parameter. There you go. And if it's higher than that, then just remove the current point. We can do this, of course, inside of a pop simulation, just like outside. And this is kind of a brute force approach to just kill the points that are higher, no matter what their lifespan is or whatever. So keep that in mind. You always have full control over your points, and you can delete them whenever you want. So the next thing is, okay, those are just points. Let's turn them actually into some bubbles. So let's just copy a few points on this with a copy to points. It depends on what you want to do with it later, but I will use actually primitives because they are just spheres defined by a single point. That means they're pretty lightweight. And when we use them, we have very little geometry to work with. So as you can see, they're way too big. So we could make them smaller. Maybe do something like that. But of course, we run into the problem, first of all, that the spheres have all the same scale, which is kind of boring. So let's change this. And we can do this outside here with an attribute randomize, for example, by changing the p scale and setting a random number between, let's say, 0.1 and 1. And this doesn't seem too bad. So let's run this. But you can see a problem that comes with it. And it's a bit hard to see, to be honest, but it's a bit too erratic. Here we can see if you go frame by frame, the points are constantly changing their size. So they don't keep the same size, which feels very unnatural. Why is this happening? Well, because the attribute randomize by default is using the point number. And because we are constantly deleting points, as we've heard before, the point number is constantly changing. So that's not a good solution. As an alternative, what we can use is, instead of the point number, we use the attribute ID, because that never changes. And we can actually do this here under options. We can change the seed attribute and the idea is already set. So let's try that. And if we actually look at the result, you can see the points are now keeping the same scale over time until they die. So this looks much nicer. And actually, let's increase the lifespan, by the way, because now the points will die anyway once they reach the top. So let's put it maybe to 0.7 or something. Actually 1, who cares? So that the points are not dying inside of our bottle, which looks a bit weird. So that's better. Yeah, pretty good. So this already feels quite nice, but we have another problem, and that is that our spheres here are sometimes emitted inside of our wall. So here, for example, what can we do against that? Well, the simplest solution would be to just change the volume that we scatter in. And we can just take the geometry that we have and make it a bit smaller. So let's use a peak for that and just make our source a bit smaller. Just a bit, not too much. So maybe something like this. So this is how it looked before, and this is how it looks now. That's a bit too much. So be careful with the numbers here. You have to type them in. So ideally, this number, of course, should be as big as the maximum of your radius of your sphere. So in our case, that's a 1 multiplied by 0. Yeah, so something like this should be fine. So let's see how this looks like now. And it seems like we solved the problem. Pretty good. Now, this is pretty good. This is not too bad. We could actually stop here, but a couple of more tricks and tips. The first thing is, instead of using an attribute randomize, I would actually recommend, and this time I want to do it with a point wrangle. You can, of course, do this with a attribute noise as well, because what I want to use instead of a random, I want to use a noise. So I will take this p scale and and fill it with a noise function. Now the idea here is that the noise function is based on the position in space, and this usually looks a bit more interesting because what's happening now is, and it's a bit hard to see, but the spheres will change their scale over time. Now the problem with this is it looks a little bit boring, and that is because currently basically all the spheres seem to have roughly the same scale, and that is because our noise currently is based on the position, and our space that we're covering here is really small. So that means that there is basically not much variance in this small area of a noise. So what we can do is we can just multiply the input by 20, and that means that the variation will be higher because we make the whole noise basically smaller. So this then looks like this, and here you can see the idea behind it. When a point is maybe just follow one point and you can see it, while it travels through space, it slowly changes its size. Now it's up to you if you like that or not, but I find it makes the whole thing a bit more interesting. And if you don't like the Vex approach, of course you can do this with an attribute noise as well. Just here, make sure that you set this to float, p-scale, and then you can set it to set. And then you can here under element size make the whole thing smaller. And then you will basically, this is the same thing by making the element size smaller as we multiplying the p. So this is how you change the noise scale, so to say, and then it basically looks the same. And it's up to you if you like that or not, but I find it pretty interesting. So this is pretty cool, and we could stop here again, but let's make it a little bit harder for ourselves. And that is by changing our actual fluid so that it actually also covers the top part of our bottle here. So we just move the clip up a little bit, if I manage to do it. There it is. There you go. Maybe something like this. And then our bubbles should die up there. Now, first of all, we have to adjust our numbers, of course. So let's double check where this would be. Maybe here, and this is roughly 0, 2, 3. So let's go in and to our height killer. We change the height number here, maybe to 2, 3. Depends on your case, of course. And now the whole thing should work as well, right? But we have a problem, because now that we integrate our top part here, it goes smaller. Damn it, how do we solve this? Now, in this case, we can't get around actually using some kind of collision here. So let's actually integrate that. We have our geometry, here it is, and we don't want to be able to move outside of it. So let's just bring it in, maybe as the last input. And of course, what we need to do for this is a merge and a static object. Let's set the merge to mutual as usual, and then we use the horrible OP input path in the sub path of our static object. And what we want to grab is the last input, so the fourth, or in computer thinking, the third input. So what we get is this. And by default, keep in mind, this will of course be a volume collision, so it will look like this. Now let's see what happens if we do this, because that's not pretty. So let's see what happens, and what we get is this. Actually that is something else. What we see here is actually the collision object. So let's make sure that out of our PopNet we only get the points by singling them out. And here we now get this. And what's happening here is all kinds of random stuff. Basically, the points are emitted inside of our collision object and then immediately pushed out. This is not what we want. We want it to only collide with the surface or the wall. And this is actually one way of solving this. We just don't use the volume collision. We use the surface collision, which of course looks like this. And then the advantage here is that we have a hollow interior. Let's see how this looks like. And it's much better, but there's still a couple of problems. So first of all, it's a bit fast, but we can see that they actually, move upwards to this point there. But some points are still, kind of wacky. This is a little bit weird, because I think what's happening here is that the collision is not recognized correctly. We could try to increase basically the precision of our calculation by increasing the sub-steps, maybe to 5 or something. And this will solve the problem but it will still create a couple of weird reactions here. As you can see, some points will get stuck and all that. So while this is totally possible, I want to show you an alternative to this. And that is a pretty cool trick. We actually do use a VDB from polygons. So we go back to the volume representation. But the trick now is that we invert this. So instead of saying the interior is the collision, we can say the exterior is the collision. And we can do this with this here, invert sign. Now nothing happens other than it changes its color a little bit. And actually while we're here, let's increase the resolution a little bit. But now basically the outside is the collision and the inside is okay, so to say. And what this will result in is this, a more accurate calculation that's also pretty fast. Now we still run into one last problem before we finally finish this video. And that is, this is really cool and all, but we still have a couple of points here that are ending up because of the collision at the edge. Now, one solution would be, again, to use a peak for our collision object, would work totally fine. But another solution is actually this p-scale that we used here, we could use inside as our p-scale. So we don't set the p-scale outside, but we set it inside, and then the size of the points will be recognized by the collision. So it's up to you how you want to do it. The only problem, if we do this, we have to take into account that we need a p-scale that is absolute. So it only will work if we set our sphere to 1 and then find here a number that actually works by itself, so that the p-scale doesn't have to be multiplied with the scale of the sphere. I hope that makes sense to you. So the sphere has to be 1 and the actual p-scale is the absolute size of the sphere this way. So I just set the amplitude to 0.01 and this will just result in an even smaller p-scale that actually represents the final scale. And what do I do with this now? I can actually take this attribute noise and put it inside of my PopNet. Of course, I can't drop it here directly, but I can use a subsolver for this and drop it here so that we set our p-scale during the simulation. And the result of this is, if I run this, as you can see that the collision is now exactly correct because the p-scale of each point will be taken into account. Now, if this is too confusing to you, don't worry, you can just use a peak with the original geometry that you use for the collision, and this will be totally fine. But you know, I just wanted to look into this a little bit deeper. Yeah, and then it looks like this, and it's a bit hard to see, but here you can see it better in the wireframe. And I think we can be pretty happy with this. But one last thing, because it's always how I would finish a pop tutorial, let's add a bit of turbulence on top. So on top of our subsolver here and our gravity, we add a pop force, because I think it will make the whole thing even more interesting. So let's play around with the numbers a little bit. Let's make maybe the static object invisible for now. There you go. So how does that look like? Oh yeah, that's too strong and too big. So let's make this. Yeah, I think that's not too bad. You can see there's a little bit of side movement now, which I think makes the whole thing a bit more interesting. And also what we can do, I would like to lower the speed a little bit. You can play around with the settings to make the look even more interesting. So always keep in mind, a pop force at the end is usually a good idea. So yeah, I think we learned a lot in this example. So I hope this is helpful. Thanks very much and see you later. Cheers.